Do Friday? That doesn't sound like enough time. I think we should move it back. Yeah.
I think that's great.
Yeah, because we didn't even get a chance to try it yet. Okay. Today, this is nice timing if you're going to career fair, sort of like taking a second to reflect on like what do I actually know? Like people keep telling me to do this stuff, but what am I getting out of this material? So today we're figuring out what were like topics or ideas that we were covering in module 2. Like what have we been talking about? What's important about it? And goal is try to build a problem for quiz 2. So you can do that and submit. I think right now it says tomorrow, but we'll probably have to like push it off so that you actually have time to like look at it and have time to do it. But anyway, that's the goal for today, is come up with what is the problem. So first step, what should the problem be about? And then we can talk about what is the problem. I'll hand out like note card. I like note cards because you can kind of, it's just enough space where you can put down like a couple ideas, flip it over. Right now we're trying to figure out what would be topics or ideas. And then the next step, what's the problem for quiz 2.
Right now, he's your recruiting leader. All right, chat it is.
At least it wasn't clear from his old
Obviously, I'll wait for my students to hear stuff like that. And then share with me as soon as you have out or
Oh, thank God.
There's always people who go
So I tried to grab some of the concepts that I saw people thinking about. Degrees of freedom, great. Maybe you've heard that term before, but here we're trying to come up with like a real understanding kind of definition of it. What was inverse dynamics? Some people were kind of talking about this, at least like talking around it or like had ideas about it, but maybe not that exact word. What was that? So the first problem we did with a flywheel, where we knew how fast the flywheel was going to move, but we didn't know how much force we needed to move it. That's inverse dynamics, where all of the motion is sort of like, this is what I want to happen. Let me figure out how much force I need to make it happen. That's your inverse dynamics kind of problem. So like, motion defined, solve for F. And that would be similar to even that like slider crank kind of mechanism. We had like two bars that were moving. There we knew for the most part it's not accelerating. Like we made an assumption that we had a quasi-static solution. So MA was 0 for all the bars, and then some of the moments was 0 because it was all. And then quasi-static. And you can say the sum of the forces is 0 two ways. One is if m is really small, like if your mass is really small compared to how big the forces are, then ma has to be really small because that's just how it is. Like if m is 0, then ma is 0. Or the other way is like the changes in momentum are really small. Like a is a very small number. Like it is moving, but maybe it's not accelerating. And either way, you can kind of justify that quasi-static is fine. Did I miss anything? What else were people thinking about? No, captured the zeitgeist of section 3 as we discover the importance of dynamics in our lives. Problem, like one thing came up, terrible at like drawing gears. Yeah, it's bad. We didn't really like talk about, I mean, it was part of like reading and videos, but we didn't really do any gear problems. Like if you have two gears hooked together, do we know what to do with that? Like, why would you use two gears? What would be the point? Like, yeah. Okay, so try to get more force. So let's say we're trying to get more force out of big gear, little gear. This one, say this one's like a 30 tooth. This one's 15 tooth. So I have gear ratio 1 to 2 or 2 to 1. Where do I want to apply force? Where do I want to put in torque so that I get more torque out? Which one's going to give me? Put torque in small one, and then I get.
Force times the radial arm is going to be bigger on the one on the right because the diameter of radius is what's.
Yeah. What do we think? Put torque over here. Yeah. So torque in, torque out. Can I use a quasi-static assumption here? And my torque in is my torque out? Do I get more torque, or does it have to add up to 0? So let's take a look, right? Split it up. Kind of like that. That whatever the connecting force is from one gear to another, it's got to be equal opposite force. Yeah. Is there anything, I guess here, really we could say like this is our, oh yeah, let's do that. So it's positive torque. What do you think? Are we good so far? Or no? Because what I did was took some of the moments on this little gear.
What does that equation say?
That radius of that little gear times that connecting force plus our torque in has to be I theta double dot. Like, however, whatever our the gear itself, however fast it's increasing its angular velocity. So that this is the change in angular momentum of that gear. Can I say it's 0? What would that mean? Yeah.
I mean, 0 would mean it's not accelerating, so it's not, you wouldn't actually be putting in any force. Like, it wouldn't be moving.
It could still be moving, right? Like if it's moving constant rate, then we could say, like, here's the steady state motion, right? Or I want it to move at this given rate, so now torque in is R times FC, right? Something like that. Or even if it's like moving slowly, same thing. Like it's moving, but maybe we want this one to move slowly just to transfer torque over. So again, like a quasi-static assumption. Then what do we end up with over here? Same thing, if I used quasi-static and say the things like moving steady state or something, like and I use 2R because if one is 30 teeth, the other one's 15, then the radius has to be double. Yeah, at least if the teeth are fixed spacing apart. And if they're not, then your gears aren't designed very well. So more teeth, bigger radius you always need. It's always directly related. Oh yeah. Am I doing that right? Did I do it right? Oh, okay. Yeah, I'm looking at it. I'm just taking the ratio of my two sum of the moments equations. So torque in, so my torque out is 1/2 of my torque in. Is that right? Is that what we want? Or torque out is 2 torque in, right? So if I put in 10 Newton meters, I actually get 20 Newton meters. Things are looking good. What about for how fast everything's moving? Because that's the other thing we use gears for. It's like I wanna rotate the, like our salad spinner has cute. Oh yeah, I was calculating the salad spinner because I'm a nerd. So I was like slowly counting how many rotations the salad spinner would do while I moved the knob around. It's kind of have this like, it has one thing that you twist this way, and then the salad spinner below uses centrifugal force to get water off of your things, but I wanted to see what gear ratio it had, again, because I'm a nerd. So I rotate by time I went around one time, the salad had spun 6 times. So what's that? What would the gear ratio be there? Like what 2 gears do I need? Like 1 and 6? Yeah. So like in this case, it would be like 15 tooth and then 6 times, or whatever, 10 tooth and 60 teeth, something like that. So 6-to-1 gear ratio. So in this case, if I'm rotating the 15 tooth, so I'm putting in 10 Newton meters, getting out 20 Newton meters, how many times do I have to rotate it to get 1 full rotation in the big gear? Twice? 2 times? Makes sense? Makes sense, yeah. It's gonna rotate opposite of whatever I do, which will make trying to tighten things confusing. Like I try to twist it one way and then it untwists the other way, so now it's left-hand rule. Maybe it's a left-handed screwdriver. It'd be kind of nice. You can use lefty tighty, lefty loosey. That would be confusing. I don't know how you do that one, but usually whenever you curl towards your thumb, positive, so it's like moving torque in, torque out. Because here I know like at that point where it's connected, the velocity has to be the same. Like they both have to move at the same speed, otherwise there's some kind of gear slipping. And that VC, this one is R times theta 1 dot, and this one is 2R theta 2 dot. So theta 2 dot so it's moving at half speed. If I'm twisting at 1 rotation per second, it's only doing half a rotation per second. So gears are good. All right, cool. Anyway, we spent a long time on that just because gears are fun. What else were people thinking about for like quiz number 2? Let me check in, because I've been talking for a while. Or keeping track on the note card. Okay. Nice.
Give us like a bunch of linkages, or I don't know, it doesn't even have to be linkages, I guess, it has degrees of freedom.
Okay, yeah, just identifying like constraints using degrees of freedom.
Yeah, or we
Okay.
can just do one, like 4 more linkages.
Yep.
I guess we could do more like the wheel problems.
Yeah. Yeah.
Reverse. Is that reverse dynamics?
Yeah, like that inverse dynamics.
Yeah, inverse.
Like we know what we wanted to do, we just didn't figure out how to do it.
Right.
Yeah, and we'll get to more. Okay. Yeah. Okay. Yeah, coming up with constraint equations. I see we make the same assumption that quasi-static, there is no motion as any of those. Yeah. Yeah, I think usually
They use the same topic.
I'll see, trying to remember. Oh yeah. So a couple of people came up with the idea of like, hey, what if we had a system, like some kind of moving system, and we need to figure out what are the constraints on its motion, something like that. So like one thing that comes up pretty often in like automotive, not pretty often, but anyway, like if you want to connect like how does thermodynamics affect dynamics, usually dynamics is all of the like, okay, yes, in principle, you can conserve energy and make work out of heat. How do we do it? And like dynamics is answering the question like, all right, once you have that work done, what do I do with it? So in this case, we have like a big piston. It only moves up and down. And then up at the top is like a crank that's actually creating that torque so we can run our car, right? So it's taking actively like expanding gas and turning it into rotational motion or explosions. Take that explosion, turn it into rotation. So what would these like what would the constraint equations look like? Like how do you even start this process? What did we do for 4-bar linkage, I guess is a good question. Where did we start? Something with vectors, right? Just like start drawing arrows. Huzzah! Like just put one. Where would we draw like vectors for that? Any idea? Not over there. That wouldn't really help. Maybe that would be a constant, but I don't think it would help me define. Where would you draw what vectors would add up? Yeah. Yeah, and that distance would be like constant, right? All right. How about like this? What would that tell us? Yeah.
Would there also be some side force on the piston as the connecting lines move down that would cause some friction along with the piston along with the cylinder wall?
Yeah. Yeah, because that connecting rod, all it can do is create, like it's always got to, the force is always parallel to whatever angle it's at. So it will try to like twist it. That's why pistons are not like flat plates. Like ideally it would just be like a single flat plate and then there's less mass to bounce it up and down, but then it would immediately like depressurize the system as it twisted it and creates a moment on it. Not ideal. What do we, so let's write some names on these things, right? Say, oh, there we go. O, A, B. And then now I drew the vectors backwards, right? I like this way. So like RA is that the middle of our kind of flywheel to our connector arm, like where it's connected. What's this blue one coming down this way? What is that vector? AB? I think that's the statics one, like that. But what's the one that we've been using? B/A, right? What are those two at? So if I take those and add them up, what happens? Where do I end up? Because now it's like tip to tail, right? What's the final location? Where do I end up? At RB? Yeah. So as I go O to A and then A to B, I should be in the same place as going straight to B. And B is only going to move up and down. At least in this case, the way that I drew it. Here it's like inline cylinder instead of like a V8 or something. What is velocity of B equal to? What vectors? What velocity vectors? Because here, if I know position constraints, I should know velocity constraints. What are those equal to? Yeah, what do I end up with for that? Numbers? Yeah, it'll be numbers eventually. I need some numbers in there, right?
You just you take the respect to like that area, you just attach that area to all of it.
Oh, for theta? Yeah, if we want to plug in like actual L's and cosines and sines and all that. Is that what you mean? What do you think? Yeah. Just like that? Or you can say that if all the positions have to add up and they have to be equal, all the velocities also have to add up and they have to be equal. Cool. Looking good. And now we could like plug in kind of, yeah, if we want like actual, how fast do I need to spin so that B is moving up at a certain speed, like there's got to be a connection between, or we end up with like two equations, two unknowns kind of problem. If I know one thing, then I can solve for the other angles and all that. What do we think? We're coming up to the end of quiz 2 creation. Got like gears and gear ratios or linkage systems and constraints, degrees of freedom kind of talk. Where do we want to go? Do we need a different idea? Or it's like both of these are, I got it, I'm ready. Not ready? Yeah.
For like the piston, or where would you like put the angles?
If I was going to do this, what I would do is kind of say like theta 1, theta 2, something like that, so that I'm always making like a triangle. And now I end up with a angle side side. I guess that's the worst one to come up with, right? In geometry, the angle side side. Usually side angle side is better. Or angle angle side. I think AAS was better. I know. Anyway. But that was the worst one, angle side side. But we have like a triangle where, yep. And to make it easier, like we could just say, rather than two different arms, make it an equilateral triangle. Ends up being, there's other issues with it, but it's still a slider crank kind of mechanism. The weird part is that as it spins around though, your piston would go up through, like up and then back down and then up and then back down. So it would be moving by a distance of 2L or 4L, sorry. It would go down 2L and then swing up and through and go up 2L and then back down. But that's okay. We're cutting our teeth on this, just getting started. But then we have two angles that are the same, so we don't have to worry about solving for angle side side problems. How's this one? Yay, nay, like rough sort of thumbs up if we want like pistons and cranks. No, thumbs up, some thumbs up. Okay. Any thumbs down, like not ready for?
I would say it still feels a bit new.
Still new, yeah. Of like coming up with constraints,
Yeah,
like this part.
I probably wouldn't make it into a kind of put that on its side.
Okay.
Just off of them.
Yeah, I am.
It's like another example.
Okay. How about for like gears, like setting up gear ratio, like if we had two gears connected either directly interfacing or like a chain connecting them, you think we'd be able to come up with gear ratio constraints?
I think if I was given the equation with like the RFC plus the torque in, if I were given something like that, I might be able to work with it, but without that, I wouldn't really know what to do.
Oh, you wouldn't come up with free body diagram first?
Oh, I guess I could do free body.
Oh, okay. All right. Yeah. That was my like figuring out, like, could we do a free body diagram on two and then say, like, yes, moments have to add up and they're all.
Did you use, for a moment, did you use like the torque equation, like so radius times the force?
Yeah. Yep. Yeah, and for gears, for the most part, it's like radius of the gear times whatever connecting force it is. Yeah.
Because that's what I learned with torque was like in high school.
Yeah, and for gears, it's always perpendicular. Like we're always like pushing perpendicular to the motion of the gear. I mean, if you're like really into gears, then yeah, there is a combination of both pushing this way, pushing that way. There's even like a twisting, like how much the gear is trying to rotate, but that's like way deeper than we're trying to get right now in terms of like what is the gear ratio and what torque do I get?
What's the difference between RFC and torque?
Torque in would be like you apply, there's some kind of like applied torque, and then there's some kind of output torque. So saying like that there is a torque in, there is a torque out, and overall they have to be, like it has to add up to zero, like you're not.
So the beta of is the acceleration is 0.
Yeah. Like in this case, if you were thinking about this as like your drivetrain of like your engine is really, your engine would be like the big 30 tooth, and then you're trying to gear down because you want to spin real fast and then create higher torque. But before, or wait, no, you spin fast, so you would be the torque in there. Yeah. So you would be the 15 tooth creating that torque in, and then that torque out is describing like how much torque your wheels actually see from the engine. So maybe like gears, is a chain okay? Do you want to like hook a chain on there, or do you want like keep them connected? To me, it's the same problem, but I'm asking, like, do you think that it is the same problem, or is it like, no, what are you doing to us?
Like what's the chain like change? Does it change anything?
Yeah, does it change anything? No? You don't think so? Yeah, what changed? What's chaining? More points of contact? Yeah, there's more points of contact. The main thing here is like when we think about like where are the forces? It's like have like attention and attention. So it all goes back to like free body diagrams anyway. Oh, whoops, I don't know why I drew it. I should have been drawing it the same way, right? Something like that.
So that would just become the new like connecting force,
Yeah, instead of like,
the physical gears touching.
yeah. Yeah, and for the most part, it would just be like the top. Usually this one is kind of slack at the bottom. But what do you think? Yep. All right, cool. So some kind of mid-gear ratios. All right, thanks. Good luck at job fair.